In the last video, we have seen the working of weighted type DAC. In a weighted type DAC, actually DAC means you have to supply some digital input here. Example, a 3-bit number 101, and you will be observing what is its equivalent analog value. So in a weighted type DAC, since this is a 3-bit number with this is D0, D1 and D2, and D2 is the most significant bit MSB and D0 is the least significant bit LSB. So since it's a 3-bit number, you need to use 3 resistors of value R, 2R and 4R. With D2 here, D1 and D0 here, this will be connected to the negative terminal of an operational amplifier. Positive is grounded and this is a feedback resistance RF and this is the output voltage. So this is a normal weighted type DAC. Now what is the drawback or what is the main disadvantage of this weighted type DAC? As the number of bits increases, 3-bit number, you need 3 resistors of value R, 2R and 4R. As the number of bit increases, for example 1010 is a 4-bit number, so you need R1, R, 2R, 4R and 8R. As the number of bits increases, the weight of the resistors also increases, so the system becomes more costly and it will become more bulky. So this is the main drawback of R weighted type resistor type, weighted resistor type DAC. Now to overcome this drawback, there is another type of DAC which will be using only 2 types of resistors, that is one is R and another resistor is its double value, that is 2R. So if we can make a digital to analog converter using these 2 resistors R and 2R, it is called R2R ladder type DAC. In this video we will see how the circuit works. R2R ladder. So the basic idea of R2R ladder is, suppose that there is a current I is coming and there are 2 resistors of equal value. Assume that this is R, this is also R. So how the current split? The current definitely will be flowing through this branch will be I by 2 and this will be I by 2, because these are 2 resistors of equal value. This will be I by 2 and I by 2, and assume that this I by 2 current is coming here, and again there are 2 resistors of equal value R and R. Now what is the current flowing through this branch? This will be I by 4 and this will be I by 4. Okay, so this is the major principle behind R2R ladder network. You will be having 2 resistors of values, equal values, and then the current will be splitting. Instead of putting R, 2R, 4R and 8R just to get the reverse of the current, to increase the current, because the current flowing through the R will be maximum. This will be I by 2, this will be I by 4 and this will be I by 8 in weighted type resistor. The same idea is obtained here also. The maximum current flow through this, again the lesser amount of current should flow through this branch, the lesser amount of current flow through the another branch, I by 2, I by 4, I by 8, I by 16, and it goes on like that. So this is the basic idea of an R2R ladder type DAC. Now I'll draw the circuit so you'll understand clearly how this circuit works. Now this is a circuit. There is an operational amplifier here also. Plus terminal is grounded. Okay. Minus terminal, I have to connect some circuit elements here. And there is also a feedback resistance RF. And this is the output voltage V0 here. Now what are the things that we connected to the minus terminal that we have to draw? So for that, I'll be drawing a reference voltage. This is a circuit. Assume that this is called a reference voltage E reference. This is E reference. There is another resistor whose value is 2R. Okay. Another resistor is R. Here also the pattern repeats. This is 2R and this is R. Here also there is 2R and this is R, 2R, then a final 2R also. So this circuit consists of two resistors only, R and 2R. That's why the circuit is called R2R ladder. Now, and assume that there is a switch. I'll draw the connections for the switch. So initially it is connected to this terminal. Okay, this is grounded, and all these things are taken together, and it is connected and it is grounded. Now suppose that you want to convert the number 1101, so this will be D3, this is D2, D1 and D0. So I will be giving D3 here, which means when the switch is connected to this branch, this will be D3. This is D2, this is D1 and this is D0. Okay, and all these things are connected together and is connected to the negative terminal of the operational amplifier. So this is the working, this is a circuit diagram, and let's see how the circuit works. I have taken a 4-bit number 1101. I want to find out what is its equivalent analog value for this 1101. So first let me draw the current flowing through this circuit. So this is actually grounded, E reference, and this is E reference and this is 2R. So the current flowing through this branch definitely will be E divided by 2R. Okay, and this current also will be E divided by 2R, because when you calculate the equivalent circuit of this branch, when you calculate the equivalent circuit consisting of this R, 2R, R, 2R, R, 2R and 2R, definitely that value will be equal to 2R. So when I replace this, the circuit will be like this. There is a reference voltage E reference, there is a 2R resistance, this is a 2R resistance, this is the 2R resistance that I will be drawing here, this is the 2R, this one. Okay, and the remaining portion R2R, R2R and R2R, when you deduce this, you will get an equivalent resistance value of 2R. Okay, so the current will definitely will be E reference here, there is a 2R resistance, so the current will be E divided by 2R here. Here also the current will be E by 2R, just like I have shown you that when there is a current I comes here, this will be I by 2 and this also will be I by 2. Similarly, this is a reference voltage E reference, this is 2R resistance, so the current flowing through this branch is E by 2R. The same current will be flowing through the another branch also, because the equivalent resistance definitely will be equal to 2R. So if you don't understand how to calculate the equivalent resistance, this is the way. This 2R and 2R is in parallel, that you will get R. R plus R definitely will be equal to 2R. 2R parallel 2R is equal to R. R plus R is equal to 2R. 2R parallel 2R is equal to R. R plus R is equal to 2R. So that's the way you get this equivalent resistance value. So the current, the final point is, the conclusion is, this is E reference, this is 2R, so this is E divided by 2R, this also will be E divided by 2R. This E by 2R current is coming here at this node, and again it is going to divide into two different paths. So by common sense we can see that this definitely will be E by 4R, this also will be E by 4R. This E by 4R current again going to split. One is through this branch, another is through, this is divided by E by 8R, this will be E by 8R. Okay, and this E by 8 is coming here, again it is splitting into two, that is E by 16R here, here also E divided by 16R. Okay, so this is the division of the current. So once again I will draw. This is a reference voltage E reference, 2R, R, 2R, R, 2R, R, 2R and 2R. Now assume that the digital voltage is applied, so you have to connect the switches to this path. This is grounded and it is taken connected to the negative terminal of the operational amplifier RF, and this is V0. Now let me write the current division also. The current here is E by 2R, here also E by 2R. The current flowing here is E by 4R. Sorry. E by 2R. So E by 2R, the current will be splitting into two. One is E divided by 4R. This also E by 4R. This E by 4R is again splitted into two. E by 8R. Here also E divided by 8R. This again splitted into two. E by 16R. This is E divided by 16R. So this is D3, D2, this is D1 and this is D0. Okay. So the current flowing here is, let me call I3. This I3 is equal to E by 2R. And this current flowing through D2, let me call this is I2, and this I2 is equal to E divided by 4R. This is I1, which is equal to E divided by 8R, and this is I0, which is equal to E divided by 16R. Okay. So this current I3 plus I2 plus I1 plus I0 is the current flowing through the negative terminal of the operational amplifier. Now for this operational amplifier, what is the output voltage? Now operational amplifier, we know the output voltage V0 is equal to, since the plus terminal is connected to ground, minus terminal potential is also 0 because of virtual short. So the output voltage is equal to 0 minus, assume that I total is the current flowing through this branch. So what is the voltage drop? 0 minus I total into RF is the output voltage, because the total output voltage here V0 equal to, here the voltage is 0. So 0 minus the drop across the resistance, 0 minus IT into RF is the output voltage V0. Now what is IT? IT is equal to, what is IT? IT is the current coming here. This is the sum of I0 plus I1 plus I2 plus I3. IT is equal to I3 plus I2 plus I1 plus I0. Now what is I3? I3 equal to E by 2R. I2 is equal to E by 4R. I1 is equal to E divided by 8R. And I0 is equal to E divided by 16R. So that's the value of I total. Now the thing is, you need to substitute this value here and you find out what is the output voltage. So when you substitute that value there, the output voltage will be is equal to minus of E by 2R plus E by 4R plus E divided by 8R plus E divided by 16R into RF, which is equal to minus RF divided by R into E by 2 plus E by 4 plus E divided by 8 and E divided by 16. So this is the expression for the output voltage. So here also, according to the MSB and LSB positional weight, we are dividing the current. Depends on the positional weight by using two resistors only, R and 2R. So this is the advantage of R to a ladder circuit. Any number of bits we can implement this DAC with the help of two resistors R and 2R. That's why this DAC is called R to R ladder circuit.